Hello everybody. I am trying to figure out how to do a video with the key so that you're not just looking up answers and they don't make sense. Okay, so this is the exam 1 from fall 2019. I'll be going over all the questions and identifying correct answers. So, the first question is to find the relationship between the two pieces here. If you just count carbons, you realize this is 1, 2, 3, 4, 5. Here it's 1, 2, 3, 4. So, they have different molecular formulas. If I'm looking between these two, on number 2, all that happens is the electrons came in from the oxygen to that bond, therefore they're resonance structures. If I'm looking here, I can see I have 1 degree of saturation. I have 1, 2, 3 carbons. 1, 2, 3 carbons. 1 oxygen, same amount of hydrogen because they're 1 degree of saturation. So they are going to be constitutional isomers. Which of these compounds does not have a dipole moment of 0, meaning that it has a dipole moment? That's water. Everybody else, all those vectors cancel out. Right? Water's a polar molecule, has a dipole moment. What are the formal charges on the nitrogen and the starred oxygen? So the nitrogen has 5 valence electrons, subtract 0 lone pair electron, subtract 4 bonds. Nitrogen has +1. The starred oxygen has 6 valence electrons, subtract 4 lone pair electrons, subtract 2 bonds. That's 0. The correct answer is D. Which of the following has an sp2 hybridized carbon, meaning it has only 3 different things and a possible lone pair? The only thing that has that is this one, because this has 1 lone pair plus 3 hydrogens. This has a radical plus 3 hydrogens. Which carbon is in the following compound are sp3 hybridized? That would be 4 and 5. How many carbon-carbon sigma bonds are in the following compound? Is that the same compound? I think they're talking about the compound above. So it would be how many carbon-carbon sigma bonds? 1, 2, 3, 4. So there's 4. And then drawing the line structure of that. Be zigzag. Whoops. We undo that. Delete. We go boom, boom. So we have a zigzag. Here we have the double bond O. And once we get to our, then we're going to go 1, 2, 3. And then we're going to have 1, hold on. Let me delete that so we have some more space. Here we go. And I'm going to start on the back end. 1, 2, 3. I have a carbon coming out. That's number carbon 3. Boom. Boom, boom, double bond O. This was also to make sure that you guys understood alkynes are linear, because people do some crazy stuff. Which of the following Lewis structures is correct for C2, CH2N? 2. So I'm probably going to have a double bond here. Let's see what we can immediately erase. This we can immediately erase. We're not putting -3 and +3 charges. Here we can immediately erase because there's too many bonds to that nitrogen. Here we can immediately erase because there's not enough electrons on the carbon. Same here, so it would be A. What is the product of the following acid-base reaction? This is my acid, this is my base. So therefore this loses the proton, this gains one. There should be a plus charge on the NH4. It's printed a little weird, but it is that one. A buffer is used to make human blood. Which acid-base pair is the buffer? So we know it can't be this, can't be D because you can't have a strong base. So you also can't have a strong acid, so it can't be B or C. For pH 7.4, it's usually the bicarbonate buffer. I don't know if we spoke that much about that. Which are favored at equilibrium? So this is a base, right? A base, and this is a carboxylic acid. So it will go towards the products, meaning it goes this way. What is the most acidic proton? Here, it's going to be number 2, because number 2 will give me the most resonant structure. And there's a lot more acid and base. I'm going to cross this one out because we don't have a picture for it. Which 2 species act as bases in the acid-base reaction shown below? So we're looking for the bases. Boom, boom, boom. So as we're looking, whoops, I'm going to make this a little bit cleaner. Clearly, the H2SO4 acted as the acid, and HNO3 gained a proton. So 2 has got to be one of the bases, meaning this also has to be one of the bases. So 2 and 4. The hybridization of the nitrogen is sp2. That is actually so the electrons in here can donate and you can do some resonance. Most acidic to least acidic. This would be your most acidic. This is your least acidic. The second most acidic, second least acidic. Here you have resonance, so since it's a cation, you only have to move one thing. Plus, and then if I can get a different color, Let me see, can I get a different color? Ah, oh, there we go. Maybe, no, I can't do that. That's what I just did. Okay, we could also move within the ring. So this can go, and then you'll have, and here's your nitrogen, and this would still all be the same. Boom. So then you would have in the ring, boom, jump, boom, with a double bond here, a plus charge here, the nitrogen, double bond and double bond. And then you can also move within the ring, doom to doom, to da. And then you can also wind up also moving that other double bond. Okay. Draw the mechanism for the reaction of sodium hydroxide with phenol. This is your base. Pulls off this proton. From the hydrogen it goes to from the bond it goes to the oxygen. The products will be O minus. I'm not going to draw the lone pairs because they don't come out very nicely. And H2O. Draw hydrogen bonding between fluorine and diethyl ether. So this is going to be the H bond acceptor. And this is the donor. So now, boom, boom, boom. And then all I do is show lines H and F. That's all it is. Okay, are there any aromatic hydrocarbons? Yes and yes. And this is a typo. This should have been O2. So if you use that, there will be no degrees of saturation. And you can come up with a bunch of different things, starting with 1, 2, 3, 4 OH. I can move the OH a bunch of places. Delete. They want to think for me. I don't really like that. I can move an OH here. I can make something where I have an OH here. And I can make something, delete, where I have an OH here and a methyl here. I can also do ethers. So there's a bunch of things you can do.